Good afternoon, I'm Blake Middleton. In the envelope of this topic today about sustainable communities, one of the things I really wanted to focus on was performance-based design, specifically with high-rise buildings, and in particular passive house as a sustainable energy design protocol applied in significant scale, and the potential for the impact on reducing carbon emissions, at least in the building industry. This is an illustration of what one can expect to imagine with the amount of carbon produced by different building types. And one of the things that we always like to focus on is the idea that our urban settings are much more sustainable in terms of their carbon footprint and buildings in general. So one goes from individual buildings to singular buildings. It makes a huge difference. The big impact here for us as architects and designers and having an opportunity to make a dent in the amount of carbon emissions that are produced on a daily, yearly basis around the world is shown perhaps by this diagram. This is the annual amount of carbon dioxide produced by buildings in New York City. This is a little old information. I imagine that number has probably gone up a bit. On a yearly basis, that's a significant amount of CO2 being pumped into the atmosphere. On an annual basis around the world, I think the numbers are in the billions. So this is a huge thing. The Earth is acting as this big sort of absorber of all this carbon dioxide, but we know what the problem and the peril that goes with that means. I had to find out from a client scientist exactly how big is a metric ton, or 35.7 metric tons of gas, because I just couldn't picture it. And this gives you an idea. There's the Empire State Building down there. So if you want to imagine a volume this big being produced of gas that weighs that amount, that's an interesting sort of kind of metric. The whole idea with passive house is really to do radically more with radically less, and there's been a huge trend in the development of power use and the kind of increasing efficiencies, whether it be light bulbs or automobiles, and now in buildings with passive house, there's an opportunity to make a significant dent in that rate of energy use that is consumed by buildings, which in turn, of course, leads to carbon emissions through power plants and other sources. Passive house is interesting. It's really a performance-based design protocol, not prescriptive. So there are a lot of different ways to reach the target goals for the amount of energy used on a per square foot basis per year. I'll show you that in a second. But it's all about a high-performance building envelope, providing, with that tight envelope, producing constant fresh air to every habitable room. That requires then heat recovery from within the building and using that energy and recycling it into the building. And then what really affects designers and builders is very careful attention and quality detail work and quality assurance during the construction process. You have to have that in order to make these buildings work properly when they're built. The results are superior thermal comfort and indoor air quality. It makes a big difference in terms of fully ventilated building mechanically. The air filtration, everything that goes with it is quite something. Long-term building durability is also an interesting outgrowth of this kind of design protocol. And the most important thing here is 60 to 80% energy savings compared to a similar building type, use, and size, depending on the locations. That's a dramatic difference. The metrics, which I won't go into detail, but can be sort of summarized here in terms of the amount of energy used for heating, the amount of energy used for cooling, and the overall energy use on a kilo-BTU per square foot per year, which is identified here, which is 38.1. So this is this kind of magic number. However you get there, that's the target for the amount of energy your building needs to be able to use in order to become qualified as a passive house building. And that sounds really interesting and a challenging number, but it's a pretty hard target to get to. So we were engaged about 4 years ago to design the first residential tower as part of the new Cornell Tech campus on Roosevelt Island. This is a applied sciences campus, a series of new buildings The overall campus goal for Cornell is to reach net zero for the entire campus when it's built out in about 15 years. This is the first phase of work that's just been done. Buildings are now occupied. This is a picture of the house there on the campus. And what I wanted to just briefly touch about here is just two aspects of the passive house components. One is the envelope, and the other is the heating system within it. And some lessons learned that came out of our experience in the field. The big idea at the campus, and just to also touch on the size of this project, this is 270,000 square feet and 26 stories. And it houses about 500 students when it's up to full capacity. There are a number of goals that the university and the design team wanted to, were aspiring to, and I won't go through all of those, but nobody had ever done a building this big of this type before. There's a fairly large building in Europe, but it's smaller by about a third or so. So this is a kind of new setting, a new trendsetter, if you will, in terms of scale. The basic principles are sort of outlined in this illustration here. The whole idea is to essentially have a kind of compact building form to make the exterior, completely tight and wrapped around there. The air systems that pump air in and exchange it with the outdoor air as it's exhausting. The ability to monitor the building on a daily or by minute basis in terms of amount of energy use. And then all the components of the building inside, whether it be, in this case, kitchens, appliances, lighting, the pumps, the machinery, everything that drives the building, all have to be super efficient in the way they work. Our concept here, due to some restrictions on Roosevelt Island, in terms of transportation of materials and new construction, all that kind of thing, we had to use a panelized system, and we quickly sort of moved in that direction. We thought that one of the big virtues of the panelized system is that you had this big stretch of surface area that only would require you to kind of seal up the joints in a limited basis, and it might be anywhere from 30 feet by 10 feet tall. And so the number of surfaces that you would have to seal up on the inside could be kind of minimized. But this envelope also has to work in many other ways. A big issue with passive house is making sure there's no thermal bridging that occurs between the outside and the inside, conducting of the heat or the cold into the building, which can short circuit some of the other thermal goals that one needs to try to achieve with passive house. So we put this system to the test, a pretty conventional process actually, using various pressurizing tests. The concept behind all of this was to prefabricate it all, attach the windows, with the air barrier, which I'll talk about in a second, this about 14-inch thick wall of insulation with an R35 perimeter on average around the outside of the building, and put that through the test in the laboratory. Pass the requirements for pressurization to make sure there was no leakage in the way we were planning on assembling it, and then put it all together in the shop and send it out to the field, erect it very quickly, and enclose the whole building. The challenge with all that is, of course, that these series of panels have to be sort of lifted up around the perimeter of the building, so you're tying up the construction cranes and all that kind of thing. One of the things that was really interesting is that, well, we had this idea, and you can see in this picture here, this kind of green surface here. Well, that's the air barrier. And you'll notice that it doesn't cover the whole panel. Our original design idea was to actually do all of that in the shop and ship it all the way out to the site, and then just make some connection points and seal those up. Well, there turned out to be about 350 connection points in every floor. That was going to be a huge number and very difficult to maintain quality control. And so while the theory was to try and make it all happen in the shop and set it up so the guys in the field could then just sort of take a flap and seal it up and move right on, it was found that it was actually a lot better to peel that off, and I'll just go back for a second here, and let that be exposed, and then seal it up once it was installed. So that was one lesson learned, is that you have to be thoughtful about what's really going to happen in the field while you're making a prefabricated system in the shop. The air barrier I talked about, which is that green surface, the whole building in a passive house has to meet this air barrier test. There's a very, very low amount of air that's allowed to transmit between the outside and the inside. And there are all these documents that you make for that. Once that barrier is being installed as part of all these panels, you also have to make sure that as they're installing it in the field, they don't punch holes through that thing. And so there's a whole protocol about how to supervise the squad on the building to make sure that they don't punch holes and inadvertently make leaks in a building, because that you have to pass that air test at the late stages of the project to make sure that you don't allow any more than a certain very, very small amount of air to actually penetrate through the building. This shows a picture of this is what we wanted to be able to do: have all the air barriers sort of attached to each panel and just patch up the connection points. We discovered as we got into the process that it was actually easier to leave the insulation exposed and come in after the fact and then seal it up at this upper joint. So that was an interesting lesson out of that. We considered this all as one element, but ended up doing some field work at the same time. There's a lot of quality control issues. There were some really great monitoring devices that the contractor developed to be able to report on a daily basis and keep track of exactly what's going on. So if there was any one location in the building that was having some problems, they had a way to report that, send it to other crews at live, basically, later in the day or the next morning. A crew would know exactly where to go based on that report and make a repair or fix a condition that might not have been built quite right. The blower door test is the big sort of exciting part of dealing with a passive house, in working on a passive house, because that's where you basically seal up all the sort of main holes, the doors and the windows, make sure everything's shuttered down, some of the duct work, and then you pressurize the building. The whole idea is to find out whether you're going to meet this sort of minimum air infiltration quotient. And so we had to first test it early on just in one part of the building, one part of a floor, to see early on whether our panels were working properly and the field work was installing, the field guys were installing it properly. And this shows some of the attachments and the monitoring devices. They seal up the doors and then they turn on the fans and they pressurize the whole building, and everything was great. It turned out that partial floor was working well, which means the way they were building it was the right way to go about doing this, and then the whole team began to just work all the way up the building. Mind you, this is 26 floors, so this is going on over months, and once they had this approach to sealing the perimeter of the building, they had to get the rest of it right, because they wouldn't know, and they couldn't test every floor. They had to sort of do it incrementally. The final blower door test was earlier this year on June 3rd. The building was also pretty close to being ready for occupancy. Passive house, as I mentioned, allows a maximum of 0.6 air changes per hour, and that's sort of a hard number to sort of understand exactly what that means. But by comparison to typical buildings that are built today, it is about a good 6 or 7 times more tight or less permeable than typical construction. We ended up testing the building. It was a moment of truth. The building was done, so it better pass, and we came out at 0.15 air changes per hour, or 4 times better than the requirement, which was astonishing. We were prepared to kind of just sneak under the wire. We never knew that we'd sort of be able to pull it off that great. Another interesting lesson that came out of this project is the heating system. One of the challenges that we had, this is a VRF system, variable refrigerant flow, which is kind of like a kind of extended air conditioner, if you will. If you imagine kind of cooling and heating fluid being pumped around the building, working off a condenser, which exchanges heat with the outside. And there'd be a loop on the north side of the building, the south side of the building, and on the north side of the building. Well, this little guy right here is called an evaporator, and it would take that fluid medium and give small bursts of air, because the building's already so tight, and because you're providing conditioned air already at close to an ambient level. This device allows each individual, in this case a dormitory, so each individual student in their room, to be able to adjust the temperature up and down about 10 to 12 degrees. So your friend from South America might want it a little warmer, and you're from Greenland and you might want it a little cooler. You have a way to kind of tweak that thing. The problem that we ran into is that the market provided the smallest evaporators that they had available were what they call 1-ton capacity. What's really interesting is that the design requirements, when you get done doing all the calculations and understanding how tight the envelope is and the amount of how much energy we really only need to use to heat or cool those little spaces, turns out you only need a quarter ton. So one of the things that we ran into was having overcapacity in the building, and we tried hard to get the manufacturer to produce new units that were much smaller because there was no need to have this capacity in a building that has this robust an envelope. That proved to be a challenge, so we had this overcapacity. I think that's another interesting lesson that came out of this process for us as we finished the project. Here's a series of pictures of the building, a typical apartment, and lounge spaces and all the rest. What's interesting to me about Passive House is if you kind of look at it from afresh, it's like, how do you know it's Passive House? I don't see the Passive House. Where's the equipment? That's an interesting sort of concept that it doesn't have to look like it's a high performance envelope to be a high performance envelope. Sendero Verde, what I'm going to talk about is two more projects that we're doing right now. Kind of lessons learned from the beta test at Cornell. We are now doing a 100% affordable housing project in East Harlem on the Upper East Side, and the whole process here is how to think about scaling this up to a larger scale than what we already accomplished at Cornell. The thing I'll point out here is the residential portion of the building will be designed to Passive House standards. It's 812,000 square feet, so this building is almost 4 times bigger than the Cornell project overall, or 630,000 square feet of affordable housing alone. That's the component that will be designed to that standard. These are some preliminary perspectives showing the building with a central court that runs through there. It's actually 3 buildings, 1, 2, 3, going to be built in quick succession with each other. It contains a charter school, a YMCA, Mount Sinai has clinical outpatient services in the building, and Union Settlement also. So very interesting kind of community partners coupled with this affordable housing, almost kind of a full block neighborhood in a way. This is interesting to me because it's really thinking about how to do high tech in low tech. So this building, because it has to be affordable, it doesn't have the kind of budget that Cornell had available at the time, is looking at building this in a much more conventional way, which is essentially block on plank or concrete masonry units, very low tech. This is typical for affordable housing, and using one of 2 products, a self-adhering air barrier or a liquid applied air barrier. These are fascinating kind of the chemical properties of these air barriers now, which are permeable, so they allow some vapor to escape out, which is what you want, but it keeps the rain and everything else from getting in. So essentially it's a weatherproof barrier, but it can be rolled on, just like paint. And achieve that same sort of capacity of reducing the air changes, just like that green panel paper that I was showing you on the Cornell project. An interesting sort of side experiment went with this thing was to figure out whether there was a way to do this with a vertical PTAC unit or a heat pump, but done in a kind of unconventional way where it would be standing in the corner of the room. You can see a picture up there. And run outdoor air, indoor, through a condenser and exhausting back out through the unit like that, and then that would work through a heat exchanger to supply heat into the room. This was engineers in the project were really excited about this because they, wanted to see if we could go about it without using VRF. We got a hold of one of these things. We built a full mock-up here, plugged it into the outside of the wall, turned it on, and the problem is the thing leaked like a sieve. So we decided we had to stick with the sort of the more conventional system, but it just shows that every project, you can have different mechanical or heating systems and still try to achieve the sort of Passive House standards. The last project I want to talk about is a project that's underway now in early design phases in Boston. It is a 1.3 million square foot project of office and residential. The office component, which is about 700,000 square feet, is intended to be designed to Passive House protocols. That's our target. This is a sort of interior rendering. The modern office workspace is all about sort of open connectivity to promote collaboration. The siting was interesting in this case because the main walls of the building face east and west, and so we're looking at a kind of curtain wall construction now. So this is much different than the previous 2 projects. This shows a kind of a section through here, a series of 5-foot wide units that are about 13 feet tall, triple glazing in this case, actually in all the cases that we're showing. So bringing in natural light in that kind of environment is very important, but how do you do that and still make a high performance wall? And the advantage of the curtain wall concept was that each one of these joints here could actually be sealed just by the gasketing between the two frames together, and that if those are designed properly, it could actually achieve that same low 0.6 air changes per hour minimum requirement. One of the other things that's really interesting to us is we're working with Professor John Fernandez at MIT and his group up there for some local personalized microclimate devices that might even take the amount of energy required to heat and cool a large office space down to even a smaller level, which really looks at the idea that you could have something on your wrist or on a seat that you're sitting in, and you could actually create the sense of being cooler or warmer, even if you're not physically fully cooler or warmer. So these are some prototype devices that they're looking into, and we may be prototyping these as part of our project up in Boston. The Hyperchair, which I think is really cool. Somehow it has sort of heat sensors and can kind of cool and heat at the same time. So where are we headed? I think there's some interesting metrics just to to think about. Passive House right now is mostly still single-family residential buildings. And a much smaller slice of that pie ends up being sort of larger commercial projects. It says one high-rise there. I think that was our project from last year. And of that group there, these tend to be more schools and hospital civic buildings. But more office buildings and other users are adopting this design protocol. These are some very large residential projects underway around the country. This one over in British Columbia. So the sort of impact on aesthetics is an interesting subtopic in this whole world. Does Passive House have to look like a Passive House, or can it look like a more traditional building? The answer is probably the latter. This is also interesting to sort of see the track of what's going on here in terms of the number of new Passive House projects ascending. This is 2016 and onwards, so you can start seeing this sort of curve rising, and more importantly, the amount of square footage that's being built to this design standard, at least in North America. And that arc is going to continue up based on everything that we sort of have been seeing and following. What does it mean for designers? It's thinking about now, I think, at least from my point of view, it may ask us to start designing walls again instead of just skins. One thinks of sort of the history and tradition of architecture up until the 20th century, where the amount of glazed openings or non-glazed openings in buildings were probably down in the 10 to 15% at best, and now we're doing buildings which are anywhere from 90 to 100% glass. You can achieve Passive House with a high-performance facade, and they do fantastic double skin systems and mechanical systems to support all that. And these are just a few of many examples of some very high-tech solutions to this energy use target. The problem is this stuff's also really expensive, and I guess what I just wanted to sort of leave everybody with is that there's ways to hit those energy targets, this high-performance goal, without necessarily breaking the bank. In fact, you can do it on a budget. And the cost differential continues to drop. Right now, it's somewhere between 4 to 7% additional cost over a building of the same type, size, and scale. But I see that number dropping, and I see the impact that may have on the building industry and our ability to reach these reduction of carbon emissions much more attainable, at least in our sphere, which is the built environment. And with that, I thank you.